Okay, dear students, so today's experiment will be on experiment number 2, that is power angle diagram, and here we are forming the MATLAB program for the determination of power angle diagram, reluctance power, excitation EMF regulation for both salient and non-salient pole synchronous machine. As you all know that salient is projected pole, non-salient is non-projected poles, and here we are considering the reactance value, XD, XQ value, that is quadrature as well as direct axis reactance. Okay. So with this, let us see this program. In problem itself, they specify the values of input like power, power factor, voltage, reactance values and all. Okay, and this is the power, and here EV value is there, X is the reactance. Okay, and delta values plays a very important role. Delta, because this angle of rotors, different power values we are finding here. Okay. So due to differentiate the salient and non-salient pole synchronous machine, here we are getting the power formula is that this is very important. By that we will come to know how to in program this power equation you have to remember. See, non-salient both reactance will be equal, and whereas for salient both reactance won't be equal. XD is direct axis reactance, XQ is quadrature axis reactance. Okay, both they will be equal. Okay, so now the total power you will be getting, this P will be actually E into V into sin delta divided by XD plus V square XD minus XQ sin of 2 delta divided by 2 XD XQ. This is the total power. Here in this total power, if both reactants will be equal, then this equation will be, this term will be 0, only this equation is remained. So therefore power equation for non-salient will be P is equals to E into V into sin delta divided by XD. Whereas for salient pole synchronous machine, you will be getting 2 powers because both reactants won't be equal. 2 powers you will get, 2 powers. Okay. And for non-salient you will be getting only one graph, whereas for salient 2 graphs you will get. I will show that one graph. For non-salient you will be getting only one graph. This is the graph for non-salient. Whereas for salient you will be getting 2 graph, 2 power equations are there. Okay. So with this, let us, I will start this program, how to write this. And I told input data are power, power factor, VT, XD, XQ. Okay, either you can define like this or you can write directly power P. One problem is there, power P is equals to 48 megawatt, power factor is 0.8, VT 34.64 values, XD, XQ if you take equal value or unequal depending upon salient, non-salient. So these are all the inputs, and one thing here I am writing program one below the other. So therefore this input is common for both salient as well as non-salient. Okay, if you want to write both program one below the other, then if condition you have to write. First condition, both the reactants will be equal, then it will execute for non-salient. Second condition, both reactants will be not equal, then it will execute for salient pole synchronous machine, right? Okay, let us start this program. So now I will define all the inputs, power P input, power in megawatt, power factor, VT, that is line to voltage will define, XD, XQ values I will define. Either you can write like this or direct values also you can put. Okay, I am initializing all these things, and VT, whatever this is, VT is line to line voltage, convert into phase, that is VT by root 3. Root how to write in MATLAB? SQRT. Okay, and power factor they have given in 0.8. So cos phi is 0.8. What is phi? Phi is cos inverse of 0.8. How to write cos inverse of 0.8? PFA, phi it is. Okay, either you can write PFA or PF underscore. Better you write PFA. If you are writing underscore here, then same thing below also you have to write underscore. Here underscore if you write, if you write directly PFA, it is undefined. Okay. So therefore PFA cos phi, phi is equals to PFA is equals to A cos PF. Okay. PF how much? 0.8. And these are all the same thing you have read in PSA 1 subject also. Same thing you have read in PSA 1 subject. Okay. So with this, actually that last but one chapter is there, same formulas we are already it has been given. You can go through that PSA book also. Okay, this reactive power will be Q is equals to P into tan of PFA, power factor cos phi it is. Cos phi is cos A, means nothing but inverse here. If cos phi is 0.8, how to write phi? Phi is cos inverse of 0.8. Okay, how to write cos inverse? Backside you have to write A. If you write A, then it will be cos inverse. Okay, then current will be P minus real minus reactive power, P minus JQ divided by 3 VT phase. Okay, and what is this delta? Delta is 0, 1, 180 degree. What is the meaning here? Graph is varying in between 0 to 180 degree. Okay, this is 0, 1, 180 degree. Colon you have to write. Okay, so next will be delta, whatever it is in degree, convert into radian, that is delta into pi by 180. Pi is what you will take in calculator. Don't write capital. If you write capital, it won't take. Okay, pi is small, converting into radian. All values are in radian you have to take. So this is all inputs. This input is common for all, except if you write XD, XQ equal, it will execute non-salient. If you write unequal, it will execute for salient. Okay, let us start this. If XD equals to XQ, for non-silent post synchronous machine, take this formula power P. Here we are calculating regulation and power calculation. Okay. So and we are plotting we are getting the graph in that. We are forming the graph. Okay. That is delta versus net power, because only one power for non-salient. So regulation, what you are getting, regulation power, as you know, just now I told E into V into sin delta divided by XD. E I am taking EF here. VT already we have defined phase value. Sin delta is known, XD is known. Only unknown is EF. Then how to find EF? This formula is there in PSA 1. Therefore EF is V plus J into I into XD. Remember, this J is imaginary, I is current. If this line won't execute, then sometime J will be unexpected expression. Then J is replaced by small I. Small I also imaginary, J also imaginary. And I is current. This current I am telling. This current don't write small I. It will be imaginary. Okay. I is current here. Therefore EF is equals to V plus J into I into XD. And this EF you convert into absolute value. That absolute value nothing but excitation EMF. Okay. The problem they told to find excitation EMF also. EF is their excitation EMF, and regulation is simple. No load minus full load by full load. So total power we found E into V into sin delta divided by XD. What the same power you convert into 3-phase power, 3 into power non-salient divided by 10 raised to 6. So we'll plot delta versus net power, and X label we find, and if you plot then it will gives the plot graph. In graph, if you want to write labelings, X label, Y label, legend, title and all, and these things you have to follow. If you won't type this, it will indicate plot without all these things. Okay, X label, delta degree, Y label, title. In bracket, whatever you type, that will display. Don't bahat like delta, degree, dash, like this arrow mark. Don't bahat like that. Okay. X label, in bracket, delta. Y label, 3-phase power. Plot title, power curve. Legend, non-salient, like that. Okay. And this is all about non-salient. Same thing you can go for salient, which is not equal. Not equal, this not equal to sign you will be getting in keyboard. Above tab you will be getting that keyboard. Okay. That symbol. Salient. So here one power we are writing E into V into sin delta divided by XD, because 2 powers you will get. Another power will be V square XD minus XQ sin of 2 delta divided by 2 into XD XQ. Okay. 2 powers are the 2 powers, 2 3-phase power you have to find. 2 power, regulation is what? No load minus full load by full load. These all three as just now I defined starting itself. Then what is EF magnitude? That you define, no? Here we defined EF. EF is V plus J into I into XD. EF I am writing EQ here. That is a change. EF also you can write, no problem. EF if I am writing here, same thing you can write EF also here. Okay. Here I am writing EQ. EQ is V plus J I into XQ. And what is ID magnitude? Absolute of I into sine of angle of voltage minus current. Okay. What is EF magnitude? Absolute of EQ plus XD minus XQ into ID magnitude. Okay. All these formulas you have to remember. Once we found this EF magnitude, this excitation EF, nothing but EF magnitude here. Okay. Regulation will be no load minus full load by full load. First power equation, this is second power equation, and net reluctance power will be 3 times of reluctance power. So total power salient will be first power plus reluctance power will be power salient. So net power salient will be 3 times of power salient divided by 10 raised to 6. This is net reluctance power, this is net power salient, 2 power we got. Now first plot will be delta versus net reluctance power, and second plot will be delta versus net power salient. First plot we are displaying in K, that is one color, that is black, and K it will take as a black in MATLAB actually, and R it is in red. 2 waveforms you will get, and hold on little bit time we are maintaining. This is X label, this is Y label, this is title, this is legend. Okay. So let us execute this. Just have a look this, so that will come to know. Okay. So now let us execute this program. So I will be taking over here. See the first program as here. Okay. So this is what here. This is for non-salient. Okay. XD equals to XQ. All P values, everything we have specified, and we'll execute. Let us just run this. Run the program. Okay. Once we run the program, then I'll write salient, SAL salient. Okay. Okay, so now what you have to do here, once I'll run this, so then in output you have to check it, it will display. Okay, so in output you have to check it, what it will display here, it is asking. Okay, just once again I'll run this so that it will be easy to understand. Just I'll run this. Okay, power in megawatt, how much power factor? 40, power 48, enter. Power factor is 0.8. Okay, enter. What is line to line voltage? 34.64. Okay, enter. And XD is 10, XQ is 10. Okay. So now, sorry, both values opposite are written. So better I'll clear this. Okay. So once again I'll execute this, 120 are written by mistakenly. Once again you execute this, Okay, so now power is how much here? 48. Power is 48. Okay, what is power factor? 0.8. Okay, what is line to line voltage? 34.64. in problem only they will give. We are doing non-salient, both are equal, both I am writing 10 here. Okay, so once you execute efficiency and regulation, we are getting here waveform will get here. Okay, so let us have a look this. Once we execute this, it will display the waveforms. Okay, just wait for a while so that, okay, just so it is now it is displaying waveform. Waveform, it is salient, only one graph we are getting, is it? Okay, so one graph will get in waveform, that is for non-salient. This is legend, this is title, this is y-axis, this is x-axis. This is for non-salient pole synchronous motion. Same thing will execute for salient. Just have a look this. This is salient. Okay, and one thing, either you can define like this, okay, or you can define like direct values also you can type. Instead of typing like input, direct values also you can. If you type directly, then it will execute directly. You will be getting graph. Okay, you will be getting graph. Save this and you will be getting direct graph, because direct values we have defined. Okay, for non-salient. So you will get direct graph without asking p is equals to values and all. Okay, so next you have to go for another one will be on this is for non-salient. Okay, these are all non-salient values. Okay, and sorry, salient, instead of defining like this, direct values I will put. Okay, direct values I will put here. See, I am defined all values directly. P is equals to 48.8, 34.64, 13.5, 9.33. Both are unequal. Okay, so now I will run this direct values I am taking. Okay, I will type some file name. Now I will execute this. We are getting two waveforms for non-salient. One will be red and there will be in black. Red R I am taking, black this is K I am taking. This is for non-salient. Okay, and what I will do, another way what I will tell here, in this program, just have a look this, just wait for a while. Okay, so now in graph, if you remove this title label, this whatever, this X label, Y label, legend and all, only plot it will show without graph. Only plot it will show without that labeling and all. Just I will show this. Instead of this here, better I will execute in this. Okay, I will remove this X label, Y label as well as plot. Okay, it will display plot except all labelings. Okay, the run. Okay, so just have a look this waveform. Once you run this, it will display the graph without labelings and all. Okay, just wait for a while. It will display. It is taking time to display that graph. Just have a look, otherwise I will execute this one, here one I will delete this, so that it will be easy to understand. Okay, here I am taking plot. Okay, so this one also you can execute, because we want to, yes, we are getting for salient two graphs without labeling, because I removed X label, Y label, plot, legend. Okay, if you put it, it will display that. Okay, getting what I am telling? Yes, without that also, with it will display graph. With it will display, without blank it will display. Okay, is it? This is for salient and non-salient. And one thing, if you remove all these semicolon, so all values it will display in output. So better all values, all semicolon you remove and check the values. Okay, all semicolon you remove and check the values. Okay, if you remove all semicolon, so all values it will display in output. Okay, so like just have a check it. This is regulation, efficiency, EF, everything it will display. Okay, this is all about salient and non-salient pole synchronous motion. Both we are executing. So one waveform for non-salient, salient, two waveforms you will be getting. Okay, so this is all about salient and non-salient pole synchronous machine. Okay, thank you.